Welcome back. So in the previous class, we defined complex numbers and seen how we can express different root numbers involving negative sign in terms of the imaginary unit I. So in this section, we are going to discuss the operations on complex numbers. So we'll see how we can add, subtract, multiply, and divide complex numbers. So let's get started. So let's have two complex numbers. So let Z1 given by X1 plus IY1 and Z2 given by X2 plus IY2 be two complex numbers. So let's have Z1 and Z2 as our complex numbers. So one, let's discuss about addition. So Z1 plus Z2 will be given by X1 plus IY1 plus X2 plus IY2. Then you remove brackets, X1 plus IY1 plus X2 plus IY2. Then you collect real terms and imaginary terms. So X1 plus X2, this is form our real part, plus IY1 plus Y2. This is how we get the sum of two complex numbers. And then subtraction for difference. So here in summary from this result, we see that to add two complex numbers is as good as just adding their real parts and then also adding their imaginary parts. So we can make that observation or that summary that addition of two, i.e. adding complex numbers is simply adding real parts and adding imaginary parts. Then difference. So we'll say Z1 minus Z2 will be X1 plus IY1 minus X2 plus IY2. Then remove brackets. So have X1 plus IY1 minus X2, then minus plus is minus IY2. Then collect real terms or real parts. So we have X1 minus X2 plus IY1 minus Y2. It also turns out that to subtract two complex numbers is as good as simply subtracting the real parts and then also subtracting the imaginary parts. So we can try that observation to subtract two complex numbers. Simply subtract real parts and subtract imaginary parts. So that's how we do the addition and subtraction. Then for multiplication, so you can take it in two parts. So if K is a real constant, then K Z1 will be K into X1 plus IY1, and that will give us KX1 plus IKY1. So when you have just a real constant, you multiply by a complex number, then that constant multiplies both the real part and the imaginary part. And then if you have to multiply Z1 and Z2, then we'll have X1 plus IY1 times X2 plus IY2. Now this is just like a product of two algebraic expressions. So you write this as X1 times the second complex number X2 plus IY2 plus IY1 into X2 plus IY2. And then you open the bracket, so we'll have X1, X2 plus I X1, Y2 plus Y1 times X2 will be I X2, Y1. Now, IY1 times IY2, remember that I times I is I squared, and I squared is -1. So this will give me minus Y1 times Y2, because IY1 times IY2 is the same as I squared Y1, Y2, then the value of I squared is -1. So that's why I have this minus. So then I collect parts without I have X1, X2 minus Y1, Y2 plus X1, I X1, Y2 plus I X2, Y1. So this is how we multiply two complex numbers. Now we do examples on how to do the product of how to do the first three operations: addition, subtraction, and multiplication. And then to do the division, we'll need to give a definition of a conjugate of a complex number before we can carry out that operation. So at the beginning, let's give examples for these first three operations. So let Z1 be given by 2 plus 3i, and Z2 be given by 4 plus 5i. Then Z1 plus Z2 will be given by 2 plus 3i plus 4 plus 5i, which will be 2 plus 4, the real parts, plus 3i plus 5i to give us an imaginary part. So 2 plus 4 is 6, 3i plus 5i is 8i. So that is be our Z1 plus Z2. Then Z1 minus Z2 will be 2 plus 3i minus 4 plus 5i. Then this is the same as 2 plus 3i minus 4 minus 5i. Collect real parts, so 2 minus 4 plus 3i minus 5i. So that will give us minus 2 minus 2i. So that is what will give us Z1 minus Z2. Or could have simply said 2 minus 4 to get minus 2, the real part, and then 3 minus 5 to get minus 2, I have the imaginary part. And then Z1 times Z2 will be 2 plus 3I times 4 plus 5I. Then will be 2 into 4 plus 5I plus 3 into 4, 3I into 4 plus 5I. 2 times 4 is 8. 2 times 5I is 10I. 3I times 4 is 12I. 3I times 5I will be 15I squared, but I squared is minus 1, so we'll have minus 15. So we'll have 8 minus 15 plus 10I plus 12I. So 8 minus 15 is minus 7. 10I plus 12I is 22I. So that's how we get that value. And then if I say 6Z1 is the same as 6 into 2 plus 3I, which will be 6 times 2 is 12. 6 times 3 is 18I. And if I say minus a half Z2, the same as minus a half into Z2 is given by 4 plus 5I. Negative a half times 4 is negative 2. Negative a half times 5 is negative 5 over 2I. So that's what we have. So also when I have another number, if I have just say 3 times 2 plus 4I, then the same as 3 times 2, which is 6, plus 3 times 4, which is 12I. If I have another problem, say 2 minus 7I times 3 plus 4I, then this is the same as 2 into 3 plus 4I minus 7I into 3 plus 4I. 2 times 3 is 6. 2 times 4I is 8I minus 21I. Minus plus is minus, but I times I is I squared is minus 1. So minus 1 times minus 1 is plus 1. So 7 times 4 is 28. So this will give you 6 plus 28 plus 8I minus 21I. So 6 plus 28 will give us 34. 8 minus 21 is minus 13I. And then if you have a problem like say 10 plus 6I over 2, it's just the same as a half of 10 plus 6I. A half of 10 is 5. A half of 6 is 3. So 5 plus 3I. So that's generally how we compute the sum, the difference, and the product of two complex numbers. So for us to define division, we need to first define a complex conjugate number. So let Z be X plus IY. So let Z given by X plus IY be a complex number. Then the complex conjugate, or simply just conjugate, of Z is denoted by you put a bar on top of Z, or you write Z star is the number Z bar equals to X minus IY. So what this one simply means is that to define the conjugate of a complex number X plus IY, you simply change the sign between the real parts to the real parts and the imaginary parts to be minus. So e.g., the conjugate of 3 plus 2i will be simply 3 minus 2i. And the complex conjugate of 4 minus 6i would be given by 4 plus 6i. The conjugate of minus 2 minus 3i will be minus 2 plus 3i. And conjugate of, say, minus 5 plus 6i will be minus 5 minus 6i, etc. So that's how we find, or how we define complex conjugates. And then there are some properties for complex conjugates. So I can put it in form of a theorem. So for any two complex numbers, Z1 and Z2, one, the complex conjugate of Z1 plus Z2 is the same as conjugate of Z1 plus conjugate of Z2. Maybe we can give the proof for this one quickly. So solution or proof. So you can say let Z1 be given by X1 plus IY1 and Z2 be given by X2 plus IY2. Let these be the structures of those two complex numbers, Z1 and Z2. Then Z1 plus Z2 is the same as X1 plus X2 plus IY1 plus Y2. This is what you have seen from the previous discussion. So which implies that the conjugate of Z1 plus Z2 would be the same as X1 plus X2 minus IY1 plus Y2. That's by definition. But we change the sign. If it is plus, we put minus and vice versa between the real parts and the imaginary parts. Which will be when I open the brackets, I have X1 plus X2 minus I times Y1 will be minus IY1 minus I times Y2 will be minus IY2. Then I put X1, I bring together with minus IY1, and then plus, this one is X2, I bring it together with minus IY2. And you clearly see that this part, this is actually the definition of conjugate of Z1, and this is the definition of conjugate of Z2. So i.e. conjugate of Z1 plus conjugate of Z2 is conjugate of Z1 plus conjugate of Z2. So this is the end of proof. Then part 2, conjugate of Z1 minus Z2 is the same as conjugate of Z1 minus conjugate of Z2. Please provide the proof just following the same process we have done in the first case. And then number 3, the conjugate of Z1 times Z2 is the same as conjugate of Z1 times conjugate of Z2. You can also prove that for conjugate of Z1 over Z2 is the same as conjugate of Z1 divided by conjugate of Z2. And then number 4, double conjugate of Z1 is the same as Z1 itself. Then number 6, Z is real if and only if Z is the same as its conjugate. So you see, like a number like say 6, which can be written as 6 plus 0i. When you are to, if you are to define the conjugate of 6 now, you'll be defining conjugate of 6 plus 0i, which would be 6 minus 0i. But minus 0i or plus 0i doesn't change, it remains to be the same 6. So when the conjugate of a number is the same as the same number, then that number is purely real. Number 7, Z is purely imaginary if Z is the same as negative conjugate of Z. You see, for example, a number like, say, minus 2i can be written as 0 minus 2i. So which means that when I conjugate this, it's the same as conjugating 0 minus 2i, which will give me positive 2i, or 0 plus 2i. So 0 plus 2i, which is the same as 2i. And then if I have, say, 3i, which can be written as 0 plus 3i, then the conjugate of 3i is the same as conjugate of 0 plus 3i, which will be 0 minus 3i, which is the same as minus 3i. So the original number is 3i, its conjugate is minus 3i, so the same as negative 3i is the same as the minus. So if z is minus, if z is 3i, then conjugate of z, when you negate it, then you get the same as 3i. Then real part, if real part of Z1 is the same, real part of Z1 is always the same as a half into Z plus conjugate of Z, and imaginary of Z is the same as 1 over 2i into Z minus conjugate of Z. So Z1, Z1, so 1, 1, 1. This is what we mean for these two concepts here, that we are saying that Z1 is given by x1 plus iy1. So which means the conjugate of Z1 is going to be x1 minus iy1. This is by definition. So when I say Z1 plus Z1 conjugate, I'll have x1 plus iy1 plus x1 minus iy1. And clearly you see when you add this, you get just x1 plus 2x1. Because minus i1 and plus i1 will give us, iy1 will give us 0. So this is 2x1. So which means that x1, when you make it the subject, will have a half into Z1 plus Z1 conjugate. And you know, by definition, when you write Z1 equals to X1 plus IY1, then we say that this is what we call the real part of Z1, and this Y is what we call the imaginary part of Z1. So this is to say that the real part of Z1, which is actually X1, is given by a half into Z1 plus conjugate of Z1. Similarly, when you subtract, say, Z1 minus conjugate of Z1, we'll have X1 plus IY1 minus X1 minus IY1. So opening brackets, I'll have X1 plus IY1 minus X1 plus IY1 so X1 minus X1, 0, so they'll give us 2IY1. So which means that when I make Y1 the subject, I'll get 1 over 2I into Z1 minus Z1 conjugate. So i.e. the imaginary part of Z1 is given by Y1, which is the same as 1 over 2I into Z1 minus conjugate of Z1. So now that you understand the meaning of conjugate of two complex numbers, then the division of two complex numbers can be defined. So division of two complex numbers. So to evaluate the quotient of complex numbers, Z1 over Z2, we multiply both the numerator and denominator by the complex conjugate of the denominator and simplify. So this process is called complex rationalization. So we'll demonstrate using examples to understand how to carry out this operation. So examples. Simplify the following. Leaving your answer in the form A plus BI, where A and B are so the first question is 5 plus 2I divided by 3 plus 4I. So what this one requires us to do is to write 5 plus 2i over 3 plus 4i. Then the complex conjugate of the denominator is 3 minus 4i. So we'll multiply both the numerator by 3 minus 4i. And so this, you write it as 5 plus 2i, 3 minus 4i, 3 plus 4i, 3 minus 4i. So that's what you do. And then now it turns out just to be a problem of solving product of two complex numbers. So this is the same as 5 into 3 minus 4i plus 2i into 3 minus 4i, 3 into 3 minus 4i plus 4i into 3 minus 4i. And this will give us 3 times 5 is 15. 5 times minus 4 is minus 20i. 2i times 3 is 6i. Plus times minus is minus. I times I is I squared. So we'll have minus 8i squared. I squared is minus 1. So minus 1 times minus 8 is positive 8. Then 3 times 3 is 9. 3 times minus 4 is minus 12i. 4 times 4i times 3 is positive 12i. Now 4i times minus 4i is the same as minus 16i squared, but I squared is minus 1. So minus 1 times minus 16 is positive 16. Then collect real and imaginary parts. We'll have 15 plus 8 minus 20i plus 6i over 9 plus 16 minus 12i plus 12i. So 15 plus 8 is 23 minus 20i plus 6i is minus 14i. Now you see minus 12i plus 12i cancels out. So do not have imaginary part. So just have 9 plus 16 is 25. So this will give us 23 over 25 minus 14 over 25i. Then example 2, simplify 5 plus 2i divided by I. So see that I is the same as 0 plus I. So when you say conjugate of I, we'll have conjugate of 0 plus I. So it'll give you 0 minus I. So then we'll have 5 plus 2i over I multiplied by negative I over negative I. So remember 0 minus I is just the same as minus I. So the conjugate complex number I is the same as minus I. So which will be minus I into 5 plus 2i, then minus I squared. So minus I times 5 is minus 5i, minus I times 2i is minus 2i squared over minus I squared. And remember, I squared is minus 1. So then we'll have minus 5i. Minus 1 times minus 2 is positive 2. And then minus 1 times minus 1 is positive 1. So this just be same as 2 minus 5i. Then you can give another example on the same quotients. If we have number 3, 3 over 1 plus I. So the key thing is to multiply the numerator and denominator by the conjugate of the denominator. And the conjugate in this case will be minus 1 minus I, 1 minus I, which will be 1 plus I times 1 minus I, then 3 into 1 minus I. So then you do the normal product. 3 times 1 is 3, minus 3I. 1 times 1 is 1. 1 times minus I is minus I. I times 1 is plus I times minus I is minus I squared, and I squared is minus 1. So minus 1 times minus 1 is plus 1. So this will be 3 minus 3I. And remember, the middle terms here cancels out. So minus I and positive I cancels out, and the remaining is 2. Then to write in the required form, we'll have 3 over 2 minus 3 over 2I. Then lastly, another example is 4 plus 7I divided by 2 plus 5I. So note that here we are going to multiply numerator and denominator by conjugate of the denominator, which is 2 minus 5I. So 2 minus 5I. So this will be 4 plus 7I into 2 minus 5I over 2 plus 5I, 2 minus 5I. So 4 will multiply 2 minus 5I plus 7I into 2 minus 5I. Then 2 into 2 minus 5I plus 5I into 2 minus 5I. Two times 4 is 8 minus 20I plus 14I. Then plus minus is minus, but I squared will give us minus, so it will be plus 35. Then 4 minus 10I plus 10I. Plus minus is minus, but I squared will give us a minus, so we'll have plus, then 25. So we'll have 8 plus 35, which is 43, minus 20 plus 14 is minus 6I. 4 plus 25 is 29. This middle terms cancels out. So this will be 43 over 29 minus 6 over 29I. So as an exercise, evaluate this. 3 plus I over 4 minus 2I. And then B, minus 1 plus 3I divided by 2 plus 5I. And I hope when you work out this, the answer to this one will be a half plus a half I. And the answer here will be 13 over 29 plus 11 over 29. So work out and confirm those answers. So just note that another form of this, another way someone can ask you to divide complex numbers is like a question: find the reciprocal of Z given by, say, 2 minus 3i. So reciprocal means 1 over. So to answer this, it's as good as actually finding the value of 1 over Z. So the same as 1 over 2 minus 3i. So that's what we mean by reciprocal, 1 over the number itself. So which will be now 1 over 2 minus 3i multiplied by its conjugate, 2 plus 3i, 2 plus 3i. So we'll have 2 plus 3i times 1. Then 2 minus 3i times 2 plus 3i. So it will be 2 plus 3i over 2 into 2 plus 3i minus 3i into 2 plus 3i. Then this will be 2 plus 3i over 4 plus 6i minus 6i. Minus plus is minus, but I squared is minus, so minus minus plus. So this will be 9. So this will give you 2 plus 3i over 13. Or 6i minus 6i is 0. So then you end up with 2 over 13 plus 3 over 13i. So lastly, let's define equivalence of two complex numbers. And then after definition of equality of two complex numbers, we can do an example. And, so equality of two complex numbers. So if Z equals to X plus IY and W equals to U plus IV are two complex numbers, then Z and W are said to be equal if and only if X equals to U and Y equals to V. Otherwise, they are unequal. And we write Z equals to W. So when the real parts are equal and also the imaginary parts are equal, then the two complex numbers will be said to be equal. And so that property can help us to solve some problems involving complex equations. So solve the following. So the first one is 4 plus 5i equals to Z minus 1 minus I. So solution here, we're just simply finding the value of Z. So we'll say there are two ways actually here. Method 1, you can say 4 plus 5i equals to z minus 1 minus I. So take this to the left-hand side. So we'll have z equals to 4 plus 5I, then plus 1 minus I. So which means that z will be 4 plus 5I plus 1 minus I. Then when you collect real parts, we'll have 5. And then 5I minus I is 4I. So this is one way. Then the other way is to say, method 2, we let z to be x plus iy, because this is how we write complex number. Then we'll have 4 plus 5I equals to, where the z, you put x plus yi. Remember, these are the same thing as writing x plus yi. They mean the same. Then minus 1 minus I. Then we'll have 4 plus 5I equals to x plus yi. Open brackets, we'll have minus 1 plus I. Then on the right-hand side, collect real and imaginary parts. So we'll have x minus 1 plus y plus 1 I. So which tells us that we'll have 4 should be equals to x minus 1, and 5 should be the same as y plus 1. For this equality to make sense, that the real parts on either sides must be the same. So this means that x alone will be 4 plus 1, which is 5, and y will be 5 minus 1, which is 4. So therefore, z, which is x plus yi, is going to be 5 plus 4I. So we get the same answer. And then the other equation is 1 plus 2I, z equals to 2 plus 5I. We can also do it in 2 ways. First way, 1 plus 2I, z equals to 2 plus 5I. Divide through by this bracket. So that this and this cancels out. So that z equals to 2 plus 5I over 1 plus 2I. And then this one, you do the complex sectionalization. So we'll have 2 plus 5I multiplied by the conjugate of this, which is 1 minus 2I, divided by 1 plus 2I, multiplied by 1 minus 2I. So this will be 2 into 1 minus 2I plus 5I into 1 minus 2I, divided by 1 into 1 minus 2I, plus 2I into 1 minus 2I. So we'll have 2 minus 4I plus 5I minus, so minus I squared is the same as positive 1. So 2 times 5 is 10. And then divided by 1 minus 2I plus 2I plus 4. So 2 plus 10 is 12. And then plus I divided by 5. So this will give us 12 over 5 plus 1 over 5, I as our answer. Another way, method 2, you can say let z be given by x plus yi. So 1 plus 2I z equals to 2 plus 5I. becomes 1 plus 2i times x plus yi equals to 2 plus 5i. So that now I will have 1 times x is x, 1 times yi is yi, 2i times x is 2xi, I times I is I squared, which is minus 1, so I'll have minus 2y equals to 2 plus 5i. Collecting real terms, you have x minus 2y, and imaginary parts will be y plus 2x, I equals to 2 plus 5i. And so for these two numbers to be equal, then x minus 2y should be the same as 2, and y plus 2x should be the same as 5. That's the interpretation of those two complex numbers being equal. So then we solve simultaneously. This is like now from one work. So from here, if I call this equation 1, this equation 2, from 1, x is equals to 2 plus 2y. So then I can replace this in equation 2. So I'll have y plus 2 into 2 plus 2y equals to 5. So I'll have y plus 4 plus 4y equals to 5. Then 5y equals to 1. So which means, because this one I'm getting by saying 5 minus 4. So y equals to 1 over 5. And then so x will be 2 plus 2 times 1 over 5. So 2 plus 2 over 5. When you work out 2 plus 2 over 5, you get 12 over 5. So therefore, z, which is x plus yi, is x. We have gotten the answer to be 12 over 5 plus y, I've gotten 1 over 5i. And you see that both of them give us the same value. So in the same manner, solve this. 4 plus 2i times z plus 3 minus 2i equals to 9 minus 4i. So remember, you don't have to show the method. Just pick one way of doing the problem. Either letting z equals to x plus yi, or solving it in the usual way, making z the subject and then simplifying. And when you work out correctly, this will give you 1 minus I. And then another question will be 2z minus 5z star equals to 9 plus 14i. Now remember, we said z star means conjugate of z. So here we are going to say let z be x plus yi, so which means z star is the same as x minus yi. The z star means conjugate of z. So then now 2z minus 5z star equals to 9 plus 14i becomes 2 into x plus yi minus 5 into x minus yi equals to 9 plus 14i. So open the brackets, we'll have 2x plus 2yi minus 5x minus minus is plus 5yi equals to 9 plus 14i. Then collect real terms on the left. So 2x minus 5x is going to be minus 3x. 2yi plus 5yi is 7yi equals to 9 plus 14i. So this tells you that minus 3x should be 9 and 7y should be 14. For those two complex numbers to be the same. And this simply means x is minus 3 and y is positive 2. So therefore the solution z, which is x plus yi, is equals to minus 3 plus 2i. And this becomes the solution to that given equation. So the next section will discuss different ways of expressing a complex number z and how also we plot them on a diagram we call the complex plane or the Argand diagram or the Gauss plane. Thank you.